And start recording. Recording is on now. All right. So we're on to here. Okay, so I'm going to do 8.2 today. See how far we get. I'm still able to keep the schedule somewhat. I think I'm going to start slowing down maybe even this week. I still got all these extra days here. Okay, one thing I need to let you know, yes, this is one of the results of the pandemic, I guess, as you know, as we're at home. Right outside, they're doing some tree work and it's really noisy. I know you probably can't hear it because if I took the headset off, you might be able to hear it, but I can barely hear anything. So if you try to unmute yourself, I'm almost sure I can't hear you guys. It's really noisy. All right. So, you know, I'm trying to teach and there's this, you know, thing going outside. So if we were meeting on campus, we wouldn't have this issue, I'm guessing. I don't think they try to do tree work in the middle of the day. You know, they try to avoid it, but I mean, I don't think I can exactly go outside and tell the guy to stop. I mean, he's got to do his job, I guess. So I apologize if, you know, I got all this constant noise in the background. So for sure today, if you want to let me know something, please put it in the chat. If you unmute yourself, I won't be able to hear you. Well, most of you have been doing that the semester anyway. Okay, but it's a little bit disconcerting, I guess is the word, that I'm hearing all this tree noise outside while I'm trying to lecture to you guys. Okay. All right, so we're trying to do 8.2 today. And it's 1 to 35 odd. 8.3 is actually a much more difficult section. Okay. But today we're going to introduce the graphs of the sine and cosine functions. And 8.3 are variations of it. Okay. Now remember, a long time ago, we did stuff like take a graph and we stretched it, we shrunk it, we pushed it that way, move it left, right, up, down. Okay. So we're going to be doing that today. Okay. So for introduction, for 8.2, let me first again show you the problems for those of you who don't have the book and aren't planning to get it. Okay, so on page 554, 1 to 35 odd. So it looks like the beginning was, it just says specify the period and the amplitude. So there's 1, there's 3, there's 5, there's 7. Okay, then 9 through 18, you're supposed to pick points off the graph. And then there's 19, I guess. And there's that graph, and we had to go up to 35. So I think you can see 35 now. Okay. All right, so some language. So we're gonna have the graphs of the sine and cosine function. First thing we're gonna talk about is a periodic function. Okay. A non-constant function is said to be periodic if there's a number p greater than 0, such that f of x plus p is equal to f of x. What that means is that you can take the graph and shift it. If you shift it either left or right, you end up with the same graph. Okay, the sine and cosine functions are like that. Okay, so if I pick up the graph, move it a certain amount, you get the completely identical graph. Okay, and the smallest such number is called the period of the function. Okay, so I'll show you what that means shortly. But we already know from the unit circle, if I go around a circle from last time, the graph repeats every 2 pi, right? So, you know, on a circle, if I keep going around 2 pi, you end up at the same spot, okay? Which leads us to believe that the period for the sine and cosine function are going to be 2 pi, and I'll get to that in a second. Okay, so the trig functions are all periodic. Sine, cosine, tangent, secant, cosecant, and cotangent, they're all periodic. They repeat themselves. It's as if, say, you can copy and paste a certain portion. Okay, so here is a periodic function. Okay, A is a periodic function, although it doesn't look like the trig functions. Okay, this looks offhand to me to be the sine function. Okay, just from experience. they tend to go up and down like that. Okay, so if you look at, let's say, the sine function, I'm going to cover up a portion of the graph, or it's a portion. Okay, just the stuff between the two pens in blue, that's considered one period. See how it goes up and then down and then back to zero? It goes zero. I guess it goes up to 4. It goes up to 4, down to 0, down to -4, and then back to 0. This is considered one period because if I just take that and basically copy and paste, see that thing? You see the same thing over here. You're going to see the same thing over here over and over and over. So the entire graph can be thought of as taking that piece right there and just copy and paste there and there and there and backwards. Okay, and you have that. Okay, for this graph, now this is not the graph of the sine or cosine function, but it is considered periodic. Okay, if you take a look at just between my pens, that up and down thing, kind of like upside down V, that's considered one period. Because after that, imagine copy that, paste here, right? And you just keep going like that. So here we would say the period is 6. One repeating unit is 6, okay? And then from 6 to 12, I see the same thing. And if I go backwards from -6 to 0, I see the same thing. This particular graph, it looks like the period is 2 pi. It's either a sine or cosine type of graph, okay? So the repeating unit is 2 pi. So if I pick that up and copy and paste there and go back there, every 2 pi, I get the same graph. Okay, so that's a periodic function, okay? Even though this is the definition of a periodic function, I don't think it's worth putting this down on your cheat sheet, to be honest with you. I wouldn't put that down. You can if you feel like it, but it's not necessary. Amplitude. We will be talking about amplitude, so you do want to write this down, okay? The amplitude of a function is the maximum minus the minimum divided by 2, okay? Capital M is for maximum, little m is for minimum, and you divide it by 2. Another way of saying it is the average. Okay, well, maybe I don't want to say the average, take it back. Okay, just subtract maximum minus minimum divided by 2. Okay, it looks like a formal definition, but it's actually easier when you look at a picture. Okay, in this particular graph, the maximum is 4, the minimum is -4. So how much is 4 minus a -4? If I use the formula, 4 minus a -4, that's 4 plus 4, which is 8, divided by 2, and you have 4. So the amplitude here is 4. Frankly, to be honest with you, it's easier to say if you start at 0, you go up to 4 and you go down to -4. So the amplitude is 4. Okay, it does become an issue if this gets translated, moved up or down. Okay, but this is a formal definition. You can put this on your formula sheet if you want. So amplitude is maximum minus minimum divided by 2. Capital M is for maximum, little m is for minimum. You know, maybe I'll write that down for you. Maximum, minimum. Max minus min divided by 2. Formula for amplitude. Okay. All right. You really don't need to look at all of these, at least now, but they're just trying to show you some periodic functions in real life. That looks like a period of 5.367 days, whatever that is. Okay. In physics, there's a lot of things that are periodic. Okay. There are sound waves that are periodic. So they got some pictures of different waves here. Okay. That looks like something called an oscilloscope. Okay. And you can see a sine type of function from there. It looks like they have a tuning fork that's there. And so sometimes graphs look like that or like that. Okay. Now, what do sine and cosine look like? Okay, on the top of 547, here's theta and sine data for key values going from 0 to 2 pi. If you want to put this on your cheat sheet, you may. Okay, we've seen this before though. Okay, and by the way, if we were meeting on campus, I'd make you memorize this. So, but still, it's all there. You can always derive it by drawing a unit circle. Okay, if you plot all of these on a graph, you can just take my word for it. We can go slow. So in other words, plot 0, 0, pi over 6, 1/2, pi over 3, radical 3 over 2, pi over 2, 1, and so on. You get this graph. Okay, and if you want to put this on your cheat sheet, you may. Okay, so here's the sine function. F of theta is sine of theta between 0 and 2 pi. Okay, now it's going to take too long to keep looking at pi over 6, pi over 4, and so on. The main key points we want are every pi over 2. So I want you to know for sure 0, pi over 2, pi, 3 pi over 2, 2 pi. Okay, because I'll be referring to that quite a bit. These are all correct, the pi over 6, pi over 4, pi over 3, but they kind of take too long. Okay, so the main thing for the sine function and the cosine function, okay, the period is 2 pi. You want to be able to quickly divide a graph into 4s. Okay, so for 2 pi, if you cut it in half, you have pi. Cut that in half, you have pi over 2. Half of between pi and 2 pi is 3 pi over 2. Okay, so for very quick graph, okay, just go 0, pi over 2, pi, 3 pi over 2, 2 pi. And the sign goes like this: 0 goes up to 1 at quarter of mark, halfway down to 0, 3/4 mark down to -1, and then back to 0. Okay. Again, you may put this on your cheat sheet, this one graph right here. What's over here? This is many periods. Okay. So here is one period of the sine function right there from 0 to 2 pi. And if you take that, copy and paste, you have that one there. And you have this piece over here and so on. So you have many periods. Okay. And you can see there what says 1 period is 2 pi. Okay. So you should know the sine function generally has this shape. Okay. So when you draw the sine or cosine functions for me, this should be curved like that. So don't make them straight lines. So you definitely don't want to make them jagged like something like that. Part A, it's curved. Okay. To prove it's curved, you have all the in-between points, right? But just something quick and dirty for the sine function goes through the origin. 1 period is 2 pi. So you chop this into quarters. Okay. Every one of the graphs that we're practicing right now, sine, cosine, you chop it into quarters. Okay, so half of 2 pi is pi. Half of that is pi over 2. This is 3 pi over 2. So sine starts at 0, goes up to the maximum, which is in this case is 1, 0, down to the minimum, -1, and then back to 0 when you reach 2 pi. And it just repeats itself because the period is 2 pi. Okay, again, how do you come up with this graph? Plot all these points. Just to save time, here it is. Okay, this is 0, 0. This is pi over 6, 1/2. This is pi over 3, radical 3 over 2. And plot all these, it ends up looking like this. It's curved. Okay. All right. Now, cosine on page 550. Let's look at this picture of the cosine function. How do you get this? You could make a table just like this for cosine. We've seen it before. You can make a unit circle, plot all the points. Here's what the cosine looks like. The period is also 2 pi. Where am I? Page 550. See, the period is also 2 pi. Cosine of 0 is 1. It also ends up at 1. Okay, so let's go every quarter here. So 1, pi over 2, it's down to 0. Pi, it's down to -1. 3 pi over 2 back up to 0. And 2 pi back up to 1. You can copy and paste this period, and notice they pasted that over here. Okay, so here they summarize it just for one period. So if you want to put this on your cheat sheet, you may. Once again, if we were meeting on campus, I'd make you memorize it. Okay, so cosine of 0 is 1. So for one period, if you're starting at 0, it's at 1. Okay, and then every quarter, the quarters are pi over 2, pi, 3 pi over 2, 2 pi. You always want to show me this when you're making graphs. Okay, show me the 1/4 mark, halfway mark, 3/4 mark, and then all the way through. If you can see that this is half a period, quarter of a period, half a period, 3/4 of a period, 1 period. So the cosine goes from 1 to 0 to -1 to 0 back up to 1. Okay, the domain is all real numbers. The range is bracket -1 to 1. Okay, cosine of an angle has to be between -1 and 1. And it's the same thing for the sine function. Sine function, the domain is also all real numbers. The range is bracket -1 to 1. And show you that over here, property summary on page 548. Okay, so domain is all real numbers. The range is bracket -1 to 1. Here is one period of the sine function. Okay, so again, maybe you want to put this one on your cheat sheet. Okay, so one period of the sine function goes 0, pi over 2, pi, 3 pi over 2 pi. And then just copy and paste this, keep going over here and keep going over here. It goes forever to the left and goes forever to the right. So this is what they say is the basic sine wave. See where it says 1/4 of a period, half a period, 3/4 of a period, 1 period. Okay, you'll be doing that with me over and over and over again. And quick summary of the cosine. Same thing, 1/4 of a period, half a period, 3/4 of a period, 1 period. Now, you really want to get comfortable with this because starting tomorrow, we're going to take the graph, and a long time ago we did this. We take a graph, we're going to stretch it, shrink it, move it horizontally, vertically, go this way, that way, and so on. We're going to put numbers in front of this and inside parentheses and add stuff and subtract stuff. Okay, so you want to know the basic sine and cosine functions real well. Okay, so again, here's one period of the sine function. Okay, so 0 to 2 pi, 1 period. Okay, and here are the quarter marks. 1/4 of the way is pi over 2. Halfway is pi. 3/4 of the way is 3 pi over 2. 1 full period is 2 pi. Yeah. And the sine function goes through the origin, goes 0, 1, 0, -1, 0. Yes, it has all the in-between points, but I want you to focus just on these right now. So what do you mean by the in-between points? You know, all of these guys, which come from here. Right, but I really want you to know the quarter mark, halfway mark, 3/4 mark, and all the way through. Cosine function, page 550. Period is again 2 pi. So just like the sine function, quarter mark is pi over 2, halfway is pi, 3/4 of the way is 3 pi over 2, and then 2 pi. But the cosine for one period goes from 1 to 0 to -1 to 0 to 1. Okay. I might start using the language maximum 0, minimum 0, maximum. So why don't you just say 1 and -1? But because tomorrow the maximum minimum aren't necessarily going to be 1 and -1. They might be 4 to -4 or 3 to -3. They're going to be moved. We're going to stretch it, shrink it, compress it, right? Move it, all that kind of stuff. Okay. All right, so we're going to try to get started with some of this stuff. Okay, so page 554, 8.2. Okay, this section is actually not that bad, but the next section is bad. 8.3. Okay, so I'd like to spend more time on 8.3 to be honest with you. So let's see if we can knock off 8.2 right away. Okay, so specify the period and amplitude of each function. Okay, so number 1. Page 554, number 1. I didn't really want it in red. I'll switch to a different color. It asks for the amplitude in the period. Okay, amplitude is maximum minus minimum divided by 2. So what seems to be the maximum for number 1? 1. Minimum, -1. Okay, so the amplitude is maximum minus minimum divided by 2, which is 1 minus a -1 over 2. 1 plus 1 is 2 over 2 equals 1. So very formally, if I use the formula, it's 1. Okay, but a lot of times you can just get it from the picture. Okay, from the picture, say start at 0. Okay, I go 1 up and 1 down. That's also what makes the amplitude 1. Okay, period. It's the measure of one repeating unit. Okay, sometimes it's kind of hard to tell what a repeating unit is. Okay. One way you can always do it is to go what we say is either something called peak to peak or valley to valley. Write that down. So one period peak to peak or valley to valley. What does that mean? How far is it from one high point to the next high point, or from the lowest point to the lowest point? Okay, so if I think of it that way, for number 1, peak to peak. So from here to here, right? That's a high point. That's another high point. That's one period. Okay, and if you look at that shape, which is kind of cosine-like, that is a repeating unit, because I could take that, copy, and paste, and so on. And over here, paste, and keep going. So how far is it from here to here? It's from 1 to 3, which is 2 units. Okay. So in this picture, from 1 to 3, excuse me, 2 units is my period. You can also go valley to valley from one low point to another low point. So here's a valley, here's another valley, right? Low point to low point. So if I look only at this, that is a repeating unit. So I think of that, which almost looks like a hat, I suppose, and copy and paste there, and paste there, and paste there. That is a repeating unit. So how far is it from the left valley to the right valley? That's from 0 to 2, right? And that's also 2 units, as you might guess. From 0 to 2 is also 2 units. So this is peak to peak. This one was valley to valley. So the period is 2. Now, frankly, you want to be able to get comfortable with finding the period other ways, okay? Especially when you look at the sine function. So let me go back to the sine function. Well, let me talk quickly about the cosine function. Cosine function is tailor-made. You already see a peak to a peak right here, right? In one period, you don't really see a valley to a valley unless you keep going, but that definitely looks like 2 pi. Okay. The sine function, if you only draw one period like that, you don't really see a peak to another peak. I mean, the next peak looks like it'd be over here. And for here, the next valley looks like it'd be way over here somewhere, right? Okay. Nevertheless, we know the period is 2 pi. You can also get a period by saying to yourself, okay, there has to be one section that goes up and another one that goes down. Okay, you kind of want to get comfortable with this being one period also. Okay, because they may not give you an entire peak to peak. Okay, the next one would be over here. And yes, they would be 2 pi units apart. And the next valley, the next lowest point would be way over here somewhere. You could also see they're 2 pi apart, but you don't see that, you know, you say, well, can I do that without drawing the picture? Yeah, if you can recognize this, it'd be great if you can figure this out. Say, okay, for one period, it goes up, back to 0, down, back to 0. And even now I say 0, okay, that will not be 0 necessarily if we're going to move the graph up and down like we did before. But if you can recognize this pattern, okay, that's one period. Or the graph might start down. The graph might start down and then come up to get one period, okay? So in any event, we're done with number 1. Okay, so we said the amplitude was 1 and the period was 2. Okay, amplitude is 1, period is 2. Okay, now let me show you something like number 5 though. Okay, if the context is clear, I'll abbreviate amplitude with amp and period with PER. Okay, let's look at number 5. Amplitude, the formula is maximum minus minimum divided by 2. So for number 5, what's considered the maximum? 6. What's the minimum? 2. Right? So maximum minus minimum divided by 2, 4 divided by 2, which is 2. I'm going to say something which we actually don't need now, but we'll need it tomorrow. We have a different midline. The midline is y equals 4 halfway. Okay. We're used to the midline being y equals 0, goes up and down. Here, the midline gets shifted up. You might recall a while back, in order to shift something up 4, we would have blah, 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 plus 4. So this must have get shifted 4 units up. So the midline, which used to be just the x-axis or y equals 0, is now y equals 4. The line in the middle, okay? So if I take y equals 4 and go like this, right, then you can see, oh yeah, it's 2 units up, 2 units down, which means the amplitude is 2, right? From the midline, which is y equals 4, I go 2 units up, 6, 2 units down, 2. Okay, what is the period of this function? Okay, I'll let you think about this for a moment. What's the period? You can either go peak to peak or valley to valley. This already looks like a peak. Let's go to the next peak. Right, high point, high point. So how far apart are these? 4. So my period is 4. Let's go valley to valley. Do I get the same answer? So from here to here. So how far is it from here to here? 6 minus 2, which is also 4. You can also go here to here, but then you got to do negative numbers, right? -2 minus a -6. Okay, it's still 4, but of course that's a lot more clumsy. Right? Okay, how do you do something like number 7? It can still be done. Okay, this will not be the graph of either sine or cosine. They don't look like that. Sine and cosine look like that or like that. Okay, they look like that. In fact, there's a name for that. The graph is sometimes called sinusoidal. any graph that looks sort of like that is called sinusoidal. Okay, we never say cosinusoidal. Okay, the cosine graph is sinusoidal. The sine graph is also sinusoidal. Okay, they look like that. This is not sinusoidal. Okay, but we can still do amplitude and period. So let's do it. Okay, amplitude, max minus min divided by 2. So let's see, maximum is -3. Don't like the negatives, right? Minimum is -6. So for 7, amplitude is maximum minus the minimum divided by 2, which is 3/2. Or you can say 1.5 also, I guess. What's the period? Okay, so number, where'd it go? 7? What's the period? You can go peak to peak or valley to valley. Okay, how about if I go valley to valley, here to here? So how far is it from here to here? 6 units. Suppose I go peak to peak, here to here. By the way, so can I use these? Yeah, but why use negatives when you don't have to, right? I like positives. 3 to 9. How far is it from 3 to 9? Also 6, right? So period 6. Okay, that's a basic idea. Now, what about all of these things here? So 9 through 18, you have the graph of y equals sine x. Okay, so the graph they're giving you is sine x over many periods. Okay, specify the coordinates at the indicated points. Okay, give the coordinates in terms of pi and a calculator. We're not going to fool with a calculator. Okay, just in terms of pi. Right. Well, you already know that these high points are all 1. The low points are -1. And these are all 0. Okay, so we said one period is right here. Okay, it goes up and then down. So this is considered one period. Okay, now this doesn't do the peak to peak or valley to valley for sure. Nevertheless, you kind of want to get comfortable with that being one period. Can you kind of see that's one period for sine function? Starts up, goes back to 0, down, back to 0. Okay. You also might want to think of, let's see, this is also one period. Okay. It starts down and then comes back up. Okay, so this is 0. This is 2 pi, 4 pi, 6 pi, and so on. Now, how do you find point C, for instance? Okay, well, you know the y-coordinate is 1. So if I go backwards, this is one period. That's -2 pi. This would be -4 pi. Okay, so every time I look at one of these things, that's 2 pi. So go to there, that's -2 pi. And there I add another pi over 2. Okay, so C, one more time, this is -2 pi, -4 pi, plus a pi over 2. So number 9. C is -4 pi plus pi over 2. I know the y-coordinate is already 1. Okay, it gets a little bit clumsy. Whoops, where'd it go? So over here, I know this is pi over 2, but I'm backing up negative 2 pi, another negative 2 pi. So this is negative 4 pi plus pi over 2, common denominator, times 2 times 2. So this becomes negative 8 pi. Negative 8 pi plus pi is negative 7 pi. So negative 7 pi over 2 comma 1 is that ordered pair. Okay, it's a little bit tricky, especially with the negatives and all. $13 is a little bit easier. Where's point B? So that's negative 2 pi. That's another negative 2 pi. I've backed up 2 periods. So it's negative 4 pi comma 0. So 13. Again, each of these is, our basic period is 2 pi right there. If I go backwards to here, that's 1, and that's 2 periods. Backwards. So that's negative 4 pi 0, number 13. Negative 4 pi comma 0. Okay, and how about I show you 17? I'm really doing all the hard ones. I'm doing all the negative ones, right? See, G is positive. You should like that. Well, D is also negative, but I think you can figure it out. Okay, where is E? That's half a period to the left. Okay, here is 1 complete period between the 2 pens. That's half a period. The period is 2 pi, so half a period to the left is negative pi. So E is negative pi comma 0. Negative pi comma 0. Okay, now I know it wasn't assigned, but let me do H anyway. That would be problem 16. Anything to the right should be easier. So H, way over here. All right, well, I know the y coordinate is negative 1, automatically negative 1 something. So how far is that? Okay, so that is 1 period, 2 pi, 4 pi. So I would be 6 pi, wouldn't it? That's 3 periods. Up and down, 2 pi. Up and down, 4 pi. This is 6 pi. Okay, so actually, let me do I. I is 6 pi comma 0. That's an easy one. H we know has a y coordinate of negative 1. And it's backed up quarter of a cycle. Quarter of a cycle is pi over 2. Okay, so one more time. 1 period right there. 2 pi. 4 pi. 6 pi. By the time I land at I, that's 6 pi. So I subtract a quarter of a cycle, which is pi over 2. So this is going to be, scratch paper, 6 pi minus pi over 2. Common denominator times 2 times 2. 2 times 6 is 12 pi. 12 pi minus 1 pi is 11 pi over 2. So 11 pi over 2, comma, negative 1. Okay, that's how to do those problems. 1921, state whether the sine is increasing or decreasing on the given interval. Is it going up or is it going down? Okay, increasing or decreasing. So 19, 3 pi over 2 and 2 pi. I'm going to write it like this, between 3 pi over 2 and 2 pi. We'll just look at the graph. 3 pi over 2 and 2 pi. Three pi over 2 and 2 pi. Increasing, it's going up. Okay, language. Increasing, right? Going up. Decreasing, going down, going up. Think of a roller coaster and you're moving only from left to right. If you're on a roller coaster, right here, you'd say you're increasing, decreasing, increasing. Yeah, they're trying to get you used to the language in calculus. When you get to calculus, you'll use the terminology a lot more. You know, oh, the function is increasing or the function is decreasing. So this is pre-calculus, so we're trying to set you up for that. Okay, so between 3 pi over 2 and 2 pi, looks like it's increasing. That's all. Then between 5 pi over 2 and 7 pi over 2, number 21. Oh boy, to figure out where we are. Okay, well, let's look at a sine function. Here is 2 pi. Add another pi over 2. 2 pi plus pi over 2 is 5 pi over 2. Okay, again, this is 2 pi. 2 pi is like 4 pi over 2, right? 5 pi over 2, 6 pi over 2, 7 pi over 2. So between here and here, well, we're going down the roller coaster. We're decreasing. So I'm going to say we're decreasing, definitely. Okay. All right, folks, I guess it's a good time to break. I'll just tell you, it's going to be very fast for me to finish 8.2, but I do want to sneak in some of 8.3. We're going to have to spend a lot of time with 8.3 when we start moving the graphs around. Okay, it's much, much harder to do stuff like that, right? We've touched that topic before, put a coefficient in front. What happens if we, have a coefficient in front of the x and then we're moving it left, right, up and down, and all kinds of stuff like that. Okay, so after the break, we'll do a little bit of this. We'll finish 8.2. I'll sneak in some of 8.3, and then we'll call it a day if we don't have any questions after that. But it's a lot harder to do those kind of graphs after that. Okay, so we'll stop and break until 12:10 as usual. Okay. Okay, folks, let's continue up. Again, it will not take that long for me to finish the rest of this section. In 8.3, I was just going to give you an introduction to it, and then we can spend more time on it tomorrow, and then that'll pretty much be it. And then if you want to ask questions, you can ask questions, and if not, that'll be it for today. Okay, so this was the sine function. This is going to be the cosine function. Well, if you look at the directions at the bottom there, I guess. So in exercise 23 to 32, refer to y equals the cosine of x and specify the coordinates with indicated points. Okay, so same thing. So for the cosine, again, if you're beginning at 0, it starts at the top, 1, 0, -1, 0, 1. Okay, so one period is right here. Okay. The nice thing about the cosine function is you can play the game of peak to peak, right? The high point, which is 1, to the next high point, which is also 1. Okay. So let's do some of these. 23 asks for J way over here. And let me put this on my paper here. Whoops, wrong color. Where's J? Okay, so cosine starts at the high point. So here's another high point, that's 2 pi. There's 4 pi. Okay, so again, peak to peak is 2 pi. Peak to peak is 4 pi, and plus another quarter of the way, which is pi over 2. The y coordinate is definitely 0. So it's 4 pi plus pi over 2. Common denominators, multiplied by 2, multiplied by 2. So 4 times 2 is 8. 8 pi plus 1 pi, 9 pi over 2. So point J is 9 pi over 2, comma 0. Okay. How about E? Well, that should be fairly easy. That's within one period. That's a quarter. That's the quarter mark, right? This is 0. This is 2 pi. So that's 1/4 of the way, which is pi over 2. Okay, so pi over 2, pi, 3 pi over 2, 2 pi. So E is pi over 2, comma 0. That's 27. Right, so that was pretty easy. I'll pick a -1. 31b. So it's negative. So peak to peak, from here to here, that's 2 pi. So as a point, that's -2 pi. And I back up another quarter, which is pi over 2. So it's -2 pi minus pi over 2. -2 pi minus pi over 2. Times 2 times 2. -4 pi minus pi is -5 pi over 2. All right, so point B is -5 pi over 2, comma 0. Okay. So that's about it. And then for 33 and 35, to talk about when is the cosine function increasing or decreasing. Okay, so that's sort of like the sine one. So 33 between 0 and pi. I'll write it like this. between 0 and pi. Cosine function from 0 to pi. We're definitely decreasing. You're going down on the roller coaster, right? From 0 to pi. Decreasing. Decreasing. $35. Negative pi over 2 to 0. Negative pi over 2 to 0. Well, maybe I'll just use this graph here. This is 0, so negative pi over 2 would be point D. So from D up to 0, 1, we're increasing. So I'm going to put increasing. Okay. All right, I'm actually done with what I was going to do today, but 8.2 was a much shorter section than 8.3. 8.3, we're going to pull over and park there for a while, so to speak. Okay, so even though I wasn't going to start until tomorrow, it takes a lot longer to work with that. Okay, so now we're going to do stuff to the graph. So 8.3, y equals a sine bx minus c, y equals a cosine bx minus c. I actually don't like the way that they show it, okay, which means I'm going to do it my own way. Now, what they have isn't wrong, but I'll show it to you that I think is, it piggybacks off what we said before. It's on page 560. But by way of introduction, let me show you the blue is y equals sine x. The red is y equals 2 sine x. Remember we did stretching? So the function value here was 1. If you put a 2 in front, now the function value is 2. Over here, the function value is -1. If you multiply that by 2, now the function value is -2. But notice all the zeros are the same, right? It touches the x-axis, the same spot there, there, and there. Well, that makes sense because 2 times 0 is 0. But if the y-coordinate used to be 1, then if you multiply by 2, it's up to 2. And if it used to be a -1, it's down to -2. Okay. That coefficient in front looks like it's the amplitude, right? The maximum value is 2 for the red graph. The minimum is -2. So if you use the formula, 2 minus a -2 is 4. Divide that by 2, which is 2. This number seems to be controlling the amplitude. Okay, let's look at this. Y equals cosine x. Red, y equals half cosine x. So when the y-coordinate used to be 1, now it only goes half as high. Over here, the y-coordinate used to be -1, but by putting a half there, it only goes to -1/2. But again, the zeros stay the same, which makes sense because half of 0 is 0. Okay, so this one gets stretched out. The blue graph gets stretched. If I multiply by 2, here it's kind of shrunken, right? It gets scrunched a little bit. It used to be up to here. Now it only goes as high as half. It only goes down to -1/2. Okay. So that tells me this now. So this is just an introduction to 8.3. Again, we're not really doing 8.3. I'm just giving some introduction. I'll do more of it tomorrow. Y equals a sine x or a cosine x. The amplitude is the absolute value of a. We actually have to say absolute value because this is allowed to be negative. Okay, but we want amplitude to be a positive quantity. Okay. So whatever the coefficient is in front, the absolute value of that number is the amplitude. So y equals 3 sine x, amplitude is 3. Y equals -1/2 cosine x, amplitude is 1/2. Get the idea? Let me show you a quick graph what happens in each of these cases. You've already sort of seen what happens here. Okay, you want to get comfortable with these kind of numbers. Pi over 2, pi, 3 pi over 2, 2 pi. If you need to, go ahead and put it on your cheat sheet. Although if we were meeting face-to-face, I'd make you memorize it. This is one period, right? Okay, for the regular sine function, starts at 0, maximum 1, 0, minimum 0. Okay, so the green is sine x. 3 sine x, it takes the graph and stretches it out. So 3 times 0 is still 0. So I'll do this in red, still 0. But instead of a maximum being 1, the maximum is now 3. So I can still use the language maximum 0. Minimum, the minimum used to be -1, but now it's down to -3. And back to 0. So the red graph is 3 sine x. So take the green graph, the regular sine function, and just kind of expanding it this way. Okay, so it goes up as high as 3 and goes down to -3. That's the net result of the 3. The amplitude is 3. Yes, if I just go by the formula maximum minus minimum divided by 2, 3 subtract a -3, 6 divided by 2 is 3. Okay, the easiest way to think of it is from my midline, which in this case is the x-axis, I go up to 3, I go down to -3. So this is y equals 3 sine x. The red is 3 sine x, the green is just sine x. Okay. All right, now what about -1/2 cosine x? I'm going to do that in different parts, sort of, just to piggyback off of what we did before. I'm going to call that one, it's -1. So that's -1/2 and that's +1/2. Okay, pi over 2, pi, 3 pi over 2, 2 pi. Pi over 2, pi, 3 pi over 2, 2 pi. Okay, cosine starts off at 1. So it goes 1, or I should more accurately say maximum, 0, minimum, 0, maximum. So the green is cosine x. Period 2 pi, peak to peak. Now, 1/2 cosine x. I know I put -1/2. Let's just talk about +1/2. +1/2. Well, instead of going up to 1, it only goes up to 1/2. Maximum 0. The minimum is no longer -1, it's now -1/2. 0, maximum. So that's 1/2 cosine x. Right? So it's the opposite of this one. This one stretches it out. If I multiply by 3, it goes 3 times as far. If I multiply by a half, it shrinks. It goes down by a factor of 2, right? That's like that. Now, do you recall what happens if I replace a function with its opposite? How about negative a half? That means the function value which used to be positive is now negative. The function value which used to be negative is now positive. I'm just going to reflect across the x-axis. So take the blue graph reflect across the x-axis. So this used to be 1/2 as a height. It's now there. And then 0, and then 1/2, 0, negative a half. So the red is negative 1/2 sine x, which is just a reflection of, oops, not sine, cosine, my bad. It's just a reflection of 1/2 cosine x, the blue graph, across the x-axis. Okay, so see this piece right here? The reflection will be there. This piece, which is down here, reflects over there. And this piece, which is back above, reflects down there. Okay, so the amplitude is only a half this time, right? Amplitude is 1/2. Okay, that's the way that works. Okay, I'm not going to go too much longer. I'll just show you what happens if you have a coefficient in front here, page 562, and I'll start doing problems with this tomorrow. They've got half cosine 3x, negative a half cosine 3x, and let's say basically there's a 3 in front there. Okay. One period is 2 pi over 3. All of these seem to have period 2 pi over 3. Okay, let me write that down. Y equals cosine x. Period is 2 pi. Y equals cosine 3x. Period is 2 pi over 3. Can we come up with a rule? By the way, I'll sneak in here in red a 1 divided by 1. That's still true, right? I'm trying to come up with a rule. So how about y equals cosine bx? Look at what they got here. 1, 2 pi divided by 1. 3, 2 pi divided by 3. How about b? 2 pi over b. Strictly speaking, the absolute value of b, because that's allowed to be negative, but they don't give us that many problems that are like that. We just say 2 pi over b, most times okay, but absolute value of b. So the coefficient in front of the x changes the period. Okay. By the way, this also works for sine. Okay, so let's write this in general now. Y equals sine bx or cosine bx. Period is 2 pi over absolute value of b. Very rarely, though, will they give me a negative coefficient here. So 2 pi over absolute value of b. So let me try to draw you one period of the cosine 3x function. Okay, in this case, I don't have a coefficient in front, so the amplitude is 1. It's going to go from negative 1 to 1. But the period is 2 pi over the coefficient here, 3. Okay, so how do I break that up into 4 parts? And this is not the scale necessarily. 1, -1. Okay, break it into 4. So how do I do that? First, break it in half. What's half of 2 pi over 3? 1 pi over t. I mean, half of 2 times anything is 1 of that. Then I need the quarter mark and 3/4 mark. I need half of this. Half of pi over 3. What is half of pi over 3? Pi over 6. This one might be kind of hard, but it's easier if you start counting by pi over 6s now. Okay, like this, pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. Right? Isn't 2 pi over 6 the same as pi over 3? Isn't 2 pi over 3 the same as 4 pi over 6? So this is 3 pi over 6, which is commonly known as pi over 2. Then I do my basic cosine graph. Maximum, 0, minimum, 0, maximum. And there we go. That's the way it works. Let me do a sine type, and then maybe that's going to be about it. So I'll be done in a few minutes, in which case you can ask questions, and if not, we're going to call it a day. Y equals sine 2x. So by this formula, period is 2 pi over absolute value of b, which is 2 pi divided by 2 pi. The graph finishes 1 complete period after pi, not 2 pi. How do I do that? Pi. Split into 4, half of pi. Pi over 2. Half of that. Well, half pi over 2, pi over 4. Pi over 4, 2 pi over 4, 3 pi over 4. 4 pi over 4, right? Isn't 4 pi over 4 the same as pi? And pi over 4, 2 pi over 4 is the same as pi over 2. Sine starts at 0. Maximum, 0. Minimum, 0. Here we go. Okay, now I do want to show you a contrast between these two graphs and the quote unquote regular sine and cosine graphs. So the regular sine and cosine take 2 pi to finish an entire period. This one finishes it in 2 pi over 3. It's 3 times as fast, so to speak. So if I could keep this to the same scale as before, I'll show you both of these and then I'm just about done for today. Here's 2 pi, right? 2 pi over 3, well, I'll split this into 3. Two pi over 3, 4 pi over 3, 6 pi over 3, right? Okay, now it might be kind of hard to see this, but For the regular cosine function, you would go maximum, minimum, maximum. So something like this. That whole up and down thing gets finished just right here. It's imagine you take this spring and scrunch it in until that whole period is finished right here. So that whole peak to peak finishes right there. So peak to peak is here. So halfway would be there, right? So that's one period. Here's another peak. That's the next one. Okay, so it doesn't take the graph higher or lower like the amplitude, it scrunches it in, right? Compresses it. Imagine a spring, you're taking the spring and just compressing it in. So by the time the regular cosine finishes one period, cosine 3x finishes three of them, up and down, one period, up and down, second period, up and down, three periods, whereas the regular cosine function takes the entire 2 pi to finish one period. Likewise, for sine of 2x, the regular sine function finishes in 2 pi. This one finishes in pi, i.e. you can say it's twice as fast. So I'll show you that, and then that's pretty much all I have for today. So what we're going to do starting tomorrow is graph combination of these with a different amplitude. I mean, there's a number in front of the sine or cosine, and a different period. There's a coefficient in front of the x also. We're going to have combinations of them. Here's 2 pi. Here's pi. Okay, so again, regular sine function starts at 0, halfway at 0, end of one period at 0. So maximum 0, minimum 0. That's sine of x. That whole up and down is all finished by the time I reach the pi for sine of 2x. Okay, so imagine taking this spring and scrunching it over here. So that entire up and down thing is there. One period is pi. And here's another one. So sine of 2x, from 0 to 2 pi, it completes two periods. One period, another period, whereas the regular sine function takes an entire 2 pi to finish one complete period. Okay, now we can also elongate this graph. We can make the period bigger. We're going to stretch it out. That would be the case if we have fractions here, like cosine half x or 1/4 x. And we'll see that starting tomorrow. Okay, but basically I'm just about done. I'll do my focusing thing and then that's it. So if you have any questions, you can put it in the chat. But otherwise we're going to be finished. So we're going to spend much more time on 8.3. So starting tomorrow. Okay, and again, for the calendar, we are still looking for the exam to be Thursday after we come back from spring break, Thursday, April the 8th. But I may not keep this. In fact, I'm hoping I would slow down a little bit here. The only thing I want to say for sure is that I have to finish 8.5 by Wednesday the 7th, right? Okay, but I still have all these buffer days that I can use, and we really probably want to slow down once we do more of this trig stuff. Okay, all right, I'll do my focusing thing, and then that's about it. So if you have any questions, you can put it in the chat now. And by the way, they stopped doing the tree thing in front, so if you want to unmute yourself, you can do that now if you wish. I know most of us don't really do it that much anyway. Just so you can see this in the video. Okay, so there's all that. Okay, then the back side. Okay, so we're going to start graphing like y equals 2 sine 3x, or 5 cosine of a half x tomorrow, and show you things like that. The way I'm going to do it is slightly different than the book. What the book has is correct, but to me, it's better my way. Obviously, I prefer my way. I'm obviously biased here, but there's a reason for it, because it does piggyback better from the stuff that we did before. Okay, so there's that. All right, so anybody with any questions? Otherwise, we're done for the day, folks. Okay, I don't see or hear anything, so that'll be it. All right, have a good day, everyone. We'll see everybody tomorrow. All right, and have a good day. Okay, bye, everyone.